We should probably do some questions, right? 310 homework we had went over last time. There's probably some questions from that. And then if there's any other chapter 3 related questions from the review sheet that I made up or other things, happy to knock those out after, but let's do the 310 stuff first. That'd probably be easiest for all involved, just to kind of stay organized or whatever. And then I'll talk about what I have for you guys on the asynchronous days or whatever. And that'll probably be that for today, if that sounds good to you guys. Probably enough. You guys want to start with questions then? 310 stuff, Victoria?
For 19, it says sketch the diagram like figure 5 showing the lines like the XUI.
Yeah. Okay. Yeah. Sure. Thank you.
Oh, for 19, sorry.
Yep, I got it. 19. So let me grab that. Thank you. So this is the question that Victoria's asking about. It says sketch a diagram like figure 5. Let's go and grab figure 5 real quick so we can kind of see what that looks like also. So this is figure 5. So for 19, we had that f of x is equal to 2x minus x squared. And our delta x is negative 0.4. So our delta y, well, actually, let's say this. So if our delta x is negative 0.4 and one of my x's is 2, then x plus delta x needs to be 1.6. Everybody's okay with that? So again, I'm just getting ready to make this picture. So I need x and I need x plus delta x. Victoria, is that okay so far? Okay. Now we'll do delta y, which in this case would be f of x plus delta x minus f of x, or f of 1.6 minus f of 2. So when I plug that in, I get 0.64. And I'm going to calculate dy. So dy dx is 2 minus 2x. So dy is 2 minus 2x times dx. And then if I evaluate this where x is equal to 2 and dx is equal to delta x, I get 0.8. And the tangent line, or the linearization, the linear approximation / tangent line, they both mean the same thing, that I'd be writing here when I evaluate this guy at 2, notice I'm getting -2 for the slope. So y minus 0, when I plug, yeah.
So I got -0.8. I don't know.
I think you dropped, if I plug 2 in here, I get -4, or 2 minus -4, so -2. And dx is -0.4, so I have 2 negatives being multiplied. You probably just dropped a negative somewhere in there. Okay, so let's start building out my picture now. I'm going to start by graphing f of x, which is like the blue line here in figure 5. So that's a quadratic function, right? It has x-intercepts at 0 and 2, because that's the solutions when I set that equal to 0. And its vertex is at 1, comma 1. Again, the vertex is -b over 2a. So I have 0, 0, 2, 0, and 1, 1 is like the vertex. So that's like my f of x there. And then at this tangent line, that's at the point when x equals 2, so I know that that's a point on my tangent line. And if I plug, say, 1 in for x, I get -2 plus 4, so that would be 2. So there is my tangent line. That's like this purple line. Hi. Thanks, dude. Nico, you have an appointment with the vampires. Sure thing. Yeah, I'm happy to stop and clarify what's going on.
How did you get the point? How did you get swing? Like the vertex and all of that.
So for y equals 2x minus x squared, the x-intercepts occur when I set y to be 0.
Right.
So I can factor off an x. So when I set x equal to 0, the solution is 0. And when I set 2 minus x equal to 0, the solution is 2.
This is from the red side?
Yeah. So that gives me the 2 x-intercepts there. And then my vertex is -b over 2a. So the b value is 2, and the a value is -1. So that's 1. And the y value then is I just plug 1 in for x to f of x. So there's the points for my parabola. Just doing like algebra 2 stuff.
See,
Okay, no calculus involved.
what really had me messed up was the fact that the 2x minus, it was 2x minus x squared instead of x negative x squared plus 2x.
Sure.
And that was strange.
You could write it that way also.
No, I know about
Oh, you had the a and the b as the wrong things because it wasn't written in standard form. You silly.
Yeah. That's probably something.
What's that equation where it's y b and then it's 2 times 1? What is that?
That's just me plugging the x that I found into that. Right? Is that okay? Okay. So this is x equals 2 here. And then somewhere over here is like x equals 1.6. That's 2 plus delta x. Everybody's okay with that? So this section here is my dx that's also equal to delta x. Okay. This spot is my point on dy. And then this would be my approximation using my tangent line. So everybody's still okay? Okay. So this section here is my dy. Nope, sorry. That's not. So this is like my dx. This distance here is my delta y. That's the change in y coordinate from 2 comma f of 2 to 1.6 comma f of 1.6. And this point here is like 1.6 comma L of 1.6. L is for like the linearization. Is that okay? I'm just trying to fill this in so everybody like sees what's going on here. So this distance then is my dy. Notice that the dy is an overestimate, right? Because my approximation is bigger than the actual value. So the dy should be bigger than the delta y, right? The dy is just like the difference in x to the approximation of, or the difference in f of x and the approximation of f of x plus delta x. Right? Like delta x is like f of x plus delta x minus f of x. Dy is like L of x plus delta x minus f of x. That's kind of what I'm doing there when I'm building out that picture. Notice I think I only asked you to do that one time, right, in the homework. It's kind of a hassle. Once you've done it once, it's like, okay, I get it. But it takes like a minute to kind of sort through, like, what do these things all mean again geometrically?
It's like very easy until you have to do it alone.
Yeah. Yes. Yes, that's an excellent observation, right? You watch me do it and it's like, you didn't do anything complicated there. But when you don't understand what you're doing, it's like, I don't understand what to do with these not complicated things.
Yeah, no,
So I
it's
have
like
to do
we're
it.
just
Yeah.
on watching it, it's super confusing.
Okay, I understand it. As soon as the numbers change, no.
As soon as we'll-
I think that is helpful in generating a picture, right? Like that, I think is quite helpful. And what should we observe here is that as that delta x goes to 0, delta y is going to equal dy, right? As you're getting closer and closer and closer to that point that we're building that approximation from, the better our approximation should get, right? Maybe I should do this. Right? The error in our approximation basically becomes 0. Right? The closer that like these two values get to each other, the difference between dy and delta y should become nothing, right? It should become they're the same thing. Because your approximation, when you get to delta x being 0, is just the value of the function.
So delta x being 0, meaning that doesn't mean x is 0.
Correct.
X is just getting bigger.
The change between the point you're approximating is the point that you use to build your approximation with, which is all it's going to do is spit out back the point that you had originally, which is the point on the function, which means that dy and delta y should be the same, right? Mackenzie? Same section, 3.9 number, or 3 point what? 10, 7. Sure. Victoria, was that okay? I know that took a long time doing that, but ideally it wouldn't take that long. I just wanted to make sure like I explained everything out and you guys were asking some questions, and that's good. All right, it says verify the linear approximation at a equals 0, then determine the values of x for, for which the linear approximation is accurate to within 0.1. So first thing I'm going to do, my function, my f of x in this case, is 1 or natural log of 1 plus x, and I'm interested in at 0 so the natural log of 1 is 0. Okay, so now let's build our approximation. So the derivative of natural log of 1 plus x is, that's a chain rule, so the derivative of the outside is 1 over the inside, and then times the derivative of the inside. So the slope then at 0 so there's that. So my linear approximation then is going to be just me using, well, let's write it as point slope form. That's the way I've been doing it. Y minus y1 equals m times x minus x1. So that verifies that the approximation given is correct, right? All I'm doing is building the tangent line and showing that the equation for the tangent line at 0 is x. Okay, great. Yeah, you do the same thing for 8, 9, 10, whatever. Yeah, those are just, the approximation is just the tangent line at 0. That's all you're doing to check those. It's telling you the answer, just saying check it.
Wait. So it's a show question. Got it.
Yes, but the second half is not.
Right. I have a question. So for 8, how do you know what side it's telling you to go? It's always the right side?
Well, well, if you look, the one that's a line, the equation for a line, is the linear approximation. So like mx plus b, mx plus b, mx plus b, mx plus b, those have to be the linear approximations because they're the only linear parts.
Okay.
The other parts are not linear.
Right.
Right?
Yeah.
Is that okay? These are good questions, right? All right. Now we have to do the part in green. It says to determine the values of x for which the linear approximation is accurate within 0.1. So my actual value minus 0.1 has to be less than my linearization, and the actual plus 0.1 has to be greater than my linearization, right? That's going to guarantee my linearization is in between 0.1 less than the actual and 0.1 bigger than the actual, right? That's all I've written there. And what is my linearization here in this problem?
Wait, so you didn't have to do anything with like, you just put it straight in there, you didn't have to do anything, like, negative 0.1 is less than greater to the natural log of 1 plus x, and then you move the
I mean, you could do all that work, but this is where it's going to end up,
Oh, yes.
right? You're just ending up at like, okay, it has to be like, the linearization has to be bigger than 0.1, or the actual minus 0.1, and smaller than the actual plus 0.1. So just like cut through the crap and just wrote it down what I needed. Because I'm not going to do this by hand, because yuckarooski, solving a natural log equation or inequality, like that seems like a hassle. All I'm going to do here is do this on my calculator. So I'm going to do the natural log of x plus 1 minus 1, and then x. The domain for the natural log of x plus 1 is negative 1 to positive infinity, so I'm going to start my x window at negative 1. I know that because I can't take the natural log of 0 or less, but any positive is okay.
What did you put the y to?
X.
Just x.
Yeah, because that's the linearization for this problem. And then, well, I know the natural log of 1 is 0, so I don't know, I'll just go like negative 2 to 2. It's probably enough there. And let's see what we get. So there's my logarithm. There's my linearization. Somewhere it appears to be crossing in there, but I'm going to have to do like a big zoom in there. So I'll cut this down to be like negative 1 to positive 1, and I'll probably just go from like negative 0.5 to positive 0.5. Just to get a better picture so I can see what's going on. And what I'm looking for is the linearization to be above that logarithm line. So here's my logarithm coming through again. There's my linearization, and it's always above it. Can we see that? Which is good, because that part here, this is always true, right? All real numbers satisfy that inequality. I graphed ln 1 plus x minus 0.1.
What does your window look like? Oh.
I did that, negative 0.5 to positive 0.5, and then on the x's, and then negative 1 to positive 1 on the y's.
Negative 1 and then positive 1?
Now I want to check the other inequality.
What is, what does ARN mean?
All real numbers. So there is like, that solution is, you know, all values of x that's going to be true for.
What if it wasn't below it?
Well, then it'd be, then you'd have to find the intersections. And you just want to describe the interval where it's above it,
Okay.
right? Which is what's going to happen on the next one here. So I'm just going to update this to be plus 0.1 instead of minus 0.1. So here's my logarithm. There's my linearization. And I'm interested where the linearization is below the logarithm. So it starts being below the logarithm like here, and it ends over there. So second trace, intersect command, enter, enter, and then I have to be a little bit careful with my guess. So I have to move it kind of close to that one so it finds that one first. So negative 0.383.
Are you finding the X or the Y?
I'm doing the intersect command, so I'm finding x coord. I'm only care about the x's because the question asks us to determine the values of x for which we're accurate within 0.1.
For these, you're just finding the separate parts of the line, the segment of the line that's above that X. Where
Below the X.
Yeah, it looks like I need to go a little bit further. Yeah, so again, the linearization has to be less than the logarithm. So I'm interested where the graph is below. I don't think I had it quite far enough to find that other intersection. So I moved my window out. Yeah, I was just off. So 0.56 or 0.516. And that'll do it. Mackenzie, does that feel okay?
Yeah.
Again, I wouldn't touch solving that inequality with a 10-foot pole. Like, I'm going to do that all on my calculator. That looks pretty nasty with the logarithm in there on like how to deal with that. It's probably one of those things where it's actually not possible algebraically to solve that. Or not obvious or within our capabilities. Well, that's the answer there. That's the values of x, where this approximation is accurate within 0.1. So what this is saying is if I do, if I pick a number in here like 0.1, if I do the natural log of 0.1 plus, plus 1, that should be within 0.1 of x being 0.1. So if I do like this minus this, right, I definitely fall inside of the boundary. If I pick something outside of that, though, say like 0.6, it's going to, this is the actual value. Oops, not 6. That's, well, 6 would work, I suppose, but 0.6. And then I do my linearization, or my approximation, which is just x. It's whatever I'm plugging in. And I look at the difference there, and there the linearization is bigger than or more than 0.1 off of the actual. That's all this is saying.
Yeah, I did.
Does that?
If it was different, so for if it was like 0.5, then you would just plug in minus 0.5.
Yeah. Yeah.
And then graph.
Yeah, exactly right. 100%. Precisely. Victoria?
Could you do 35?
Yeah, sure. Is this all going okay though? Like when we're doing this, do you guys understand what we're getting at?
Yeah.
And it's really one of those things like it's not hard. You just have to like get what they're asking for, right? And that's sometimes the hardest part about these is just like, you're not really, it's kind of like, what am I really doing here? And I get that. So it says the circumference of a sphere was measured to be 84 centimeters with a possible error of 0.5 centimeter. Use differentials to estimate the maximum error in the calculated surface area, and then what is the relative error, and then use differentials to estimate the maximum error in the volume. What is the relative volume? Okay, or relative error, excuse me.
I just didn't know like what equation.
Okay, so when I say circumference of a sphere, what you're talking about is like what we call a great circle. So that's a circle, a cross section of the sphere that forms a circle whose radius is also a radius of the sphere. So what I'm going to be using, circumference for a circle is 2 pi r, and the surface area for a sphere is 4 pi r squared. So I'm told about the circumference, so what I'm going to do is I'm going to just solve this circumference equation for radius. So I can then plug that into my surface area equation. So let's simplify that a little bit. Okay with that? All right. So to use differentials to get the maximum error, what I need to do is I need to calculate ds. So ds dc is going to equal 2c over pi. Everybody okay with that? Or really, ds is equal to 2dc over pi times, or I'm sorry, 2c over pi times dc. So if I evaluate that when c is equal to 84 and dc is equal to 0.5, did they say was the error? Yep. So I have 2 times 84 over pi times 0.5. And that works out to be, when I plug that through, where did I have that written down somewhere? Oh, I just wrote it as 84 over pi, which is approximately 26.74 square centimeters.
Oh, okay.
Right, I had a pi squared on the denominator. Good catch. So that's my max error. So is that okay there?
So the derivative of c to the power 2 over pi, like nothing happens to the pi.
It's a constant, so I just ignore it, right? If it was like a 7 or something. Yep. And then to do the relative error, that is like delta S over S, which is approximately going to be the same as ds over S. So 2c over pi divided by c squared over pi. Oops. 2c over pi dc, excuse me. So what's going to cancel out? What am I going to have left with? 2dc over c, right? So I'll just plug in. So there's my relative error. It's about 1 over 0.84. So that's pretty good, right? You turn that into a percentage by multiplying by 100, and that's, you know, right around 1%. Ain't too shabby. Part B asks us to do the same thing with volumes, right? So we still have that, oops. Oh, goodness gracious. That R is equal to C over 2 pi, and the volume for a sphere is 4/3 pi r cubed. So that's 4/3 pi C over 2 pi cubed. Sure. And so let's see, what can we do? That'll reduce that down to 2. One of those can reduce with one of those. So we get c cubed over 6 pi squared. Now we need to calculate dv. So dv dc is going to equal 3c squared over 6 pi squared, or just c squared over 2 pi squared. And then we'll multiply both sides by dc. And then if I evaluate that when c is 84 and dc is equal to 0.5, we get 84 squared over 2 pi squared times 0.5. And I guess we'll just type that all into the calculator. Somehow I managed to miss doing part B when I did my answers for this. But once we've done this much, it's kind of the same thing. So about 178.73. And this would be cubic centimeters. Is that better?
Yeah.
So that's, again, my max error there. And our relative error then is going to just be delta V over V, which is going to be approximately the same thing as dV over V. So dV was c squared over 2 pi squared dc, and volume is 4/3 pi, oh no, wait a minute, what was our volume? That's not how we wrote it, Mr. Kulik. we wrote it as c cubed over 6 pi squared. So let's see, what do we do? Those will reduce out. That'll reduce with that down to 3. Those will reduce down to that. So we just have dc on top. So that's going to be 3 dc over c. And again, we'll evaluate that when c is 84 and dc is 0.5. So like 1.5 out of 84. I know it's dumb writing that with a decimal, but I like leaving it that way because it makes it easy to compare to the other one. We're just like not much worse. Which I think I answered all the parts on that. I think so. Huh. Is that okay, Victoria, on what we did there? So again, if you didn't remember the surface area for a sphere, you know, like what am I going to do with that? Just FYI, I think that if you look at the inside cover of a paper textbook, it has this geometry cheat sheet on there and has the surface area for a sphere on there. So if you're ever like, ooh, boy, I don't remember that formula, that's a good place to check. Yeah, probably. I mean, I've seen it, I guess I've seen it kind of 50-50 on like the AP exam of them saying whether sometimes they'll state in the question the formula that you need, and I've seen it sometimes where they haven't. So I think it seems more recently that they are including things that are not calculus specific. Yeah. But they probably wouldn't include like the area for a square or something. Which I think you'd be good with that though. But something a little bit more obscure like the surface area for a sphere, where even you can't even make a net to like derive that on the spot. Like if it's the surface area of a box, it's like worst case scenario, you're just like, okay, there's 6 sides. What are the dimensions of 6 sides? So just added it all up. But a sphere, you can't even uncut it. It's like, what does that look like when you unfold a sphere? So it's one of those where it's like you're kind of stuck if you know it or not. Mia, what's up? Sure. Do you guys want to transition into like review stuff? Are we done with 310? Sure. Yeah, I think we have some time. Which one? 25. Okay. That's probably a good choice as it kind of covers all the different problem types I think I assigned. Probably need some directions on that. Oh boy. Okay. So the directions say use linear approximation or differentials to estimate the given number. So first thing I'm gonna do this using a linear approximation because I think it's the more natural thing to do, is I need to write a function here to describe kind of what's going on. the way I would write this particular function is I'd call this the cube root of 1,000 plus x. Why did I pick 1,000 plus x? So yeah, for this one, this would be then, I'd be interested in L of 1, would be give me that. But why didn't I do like 900 plus x or something? What? 1,000 is a perfect cube, yes. So that's why I chose to use 1,000 plus x, because when I find a point for the linearization, or to build my tangent line, I want something that's near the value that I'm inputting that'll give me a nice number to deal with. Paul?
So when I'm doing these type of problems, should I always look for like the perfect cube with the root square and then take my x and subtract that?
You should probably look for something that's like
That's always a safe bet.
easy to do arithmetic wise. Yeah. So what am I going to do? I'm concerned about f of 0. I'm going to use that as my input. So the point I'm going to be using to make my linearization is the point 0, 10. And then I need the derivative to get the slope. So again, that's a chain rule. I'm going to think about the cube root as a 1/3 power. So the derivative of the inside is 1/3 times derivative of the outside is 1/3 times the inside raised to the negative 2/3 power, and then times the derivative of the inside. And then I'm interested at what's happening at 0. So the cube root of 1,000 is 10. So 10 to the negative 2 is 1 over 100. And that simplifies down to, well, I did the cube root to change it from 1,000 to 10. And then I'm going to do the squaring after, right? So Mackenzie, what I'm thinking about is this being like 1,000 to the 1/3 to the negative 2, right? Just so it's easier for me to handle in my head. You know what I'm saying? Now, you could just type that in your calculator also, and it's fine, right? Like, you don't need to do that. So here's my tangent line. So y minus 10 equals 1 over 300 x minus 0. And I guess you could simplify this more if you wanted to, but like, I don't think you really need to. I should probably say here then. So now I can take my I do that is approximately just my linearization, my tangent line with 1 plugged in.
Why is it 1? X plus 1.
Oh, yeah. Thank you. Sure. Yep. Thank you. So 1 over 300 times 1 plus 10. So I have 10.033. And just for grins, if I take 1,001 and raise that to the 1/3. Pretty good, right? Oops, 2 zeros.
Why did we use F of 0? Just like.
Well, it's because it was going to turn out, one, it was close to what we're interested in. 0 is pretty close to 1. And then 2, I get a nice even number popping out of it, so it's just like convenient to work with.
So that's why you use F of 0?
Yeah. I mean, it was close to 1 is what I'm going to be plugging in.
So I should always pick something close to L. L of X.
Yeah.
Okay.
Yeah. Yes.
And it doesn't matter if it's exact.
Well, it's an approximation,
Okay.
right? The linearization is an approximation, so it's not going to be an exact answer. You can say the approximation is exactly this, but it's still an approximation, right? Like,
Within how much do you think I should use like for picking a number for F?
I mean, the closer you get, the better. But like, usually I'm just going to go with whatever gives me a convenient value.
Thank you.
Yeah. I mean, like, could I have done 1 plus X? Sure, but now like we're plugging in 1,000
Right, yeah.
and we're using 0 to, so that's like kind of a crummy approximation, right?
Right.
Sure. All right, Mia, you wanted to talk about something from the study guide there? Let me grab that. For D and E? Sure. So, oops. Oh my goodness. It's easy. I hate you sometimes. One note. All right. So this is like super easy, right? This point needs to lie on that curve. So all I'm doing is plugging negative 0.22 in for X and K in for Y. No, it has to line, this is the curve. So what I've highlighted, not into the derivative. Right? What does it say? It says there's a number K such that negative 0.22 comma K is on the curve, not the derivative. So I'd have like negative 0.22 squared minus 4 times negative 0.22 K plus K squared equals 13. And then you could simplify that or whatever, but like that right there is fine.
So C, you're plugging it into the tangent line, but D, you're plugging it into the curve.
Yes. So in part C, you're approximating
Using
using the
the tangent.
tangent line. In part D, you're going to actually find the value for K, the actual value for K.
And then D.
So D, we just set it up. E, we're going to solve it. So how would I solve this
Okay, then I'm fine.
on my calculator?
Okay.
Or graph the two sides and find the intersection. If it wasn't quadratic, that's what you'd have to do. But that's all we're doing.
Okay, thank you.
Yes, Victoria.
For your P or B, I think it's wrong, because I think you didn't add it.
Okay, so for B, you say?
Yeah, so.
All right, let's take a look.
When you add it to 1, it's going to be like 11 over 5, and I think it's supposed to be 13 over 5.
Oh.
Plus 1.
So that's 8 over 5 plus 1 should be, yeah, I guess you're right. So that should be 0.64 then, right? 0.84. Okay. Sure, I'll buy that.
You do 5.
5?
Just, yeah, the wording is like,
Just like all of 5.
Okay. It says as a charge on a battery is discharged, the voltage of the battery is given by the twice differentiable function h for time 0 to 10, where h of t is measured in volts and time is measured in hours. Values of h of t at selected values of time t are shown in the table below. Use the table to approximate h prime of 6. Use correct units and explain the meaning of h prime of 6 in the context of the problem. Okay? So can we calculate do we have an equation for h? No. So how are we going to do the derivative then? Slope. The slope between what points? 4 and 7, because that's where 6 is in between. It's the best we can do. So that would be what, like 51 minus 67 over 3, and then whatever that is. Is that okay with everybody? I guess we could do it. Come on. So negative 5.3 repeating. Hi. And this would be volts per hour. And what is this describing then in the context of the problem? Sure, the rate of change at 6 hours, or the rate at which the battery is losing voltage at hour 6 or whatever. Something like that would be reasonable. Part B says the charge of the battery is modeled by the twice differentiable function C from for time 0 to 10, where C of t is measured in degrees voltage. I don't think that was supposed to, I think it's just in voltage. And time t is measured in hours. It is known that C of 4 is equal to 67. That's in the table. And the derivative of C is given by C of prime of t equals negative 10 e to the negative 1 point, or negative 0.1 t.
Is it supposed to be H or is it C?
Oh, no, C is something. Okay. So H, what do I want to say here? So C is a model for the data in the table. C is not the same as H. It's the model that would be like if we did an exponential regression. That might be what C is. Could be something like that. If we took all the data and used the exponential regression, we could build that. That's basically what we're saying there. Is that okay, Mackenzie? Okay. So again, C is an approximation of the function H. Right? It's not exactly, but it's an approximation. Based on the model given, at what rate is the temperature changing at time t? So what am I going to do here? I'm going to build a tangent line for C and use that to give me the voltage at time 3. Everybody's okay with that? So I'm building a linearization. So my linearization, the y coordinate is going to come from, I'm going to use this piece that I know was part of C. Right? And then to find M, I'm going to just use C prime of 4.
So we plug 4 in the cup.
I need to use 4 because that's the point that I'm finding the tangent line at.
Right.
Right? So all I'm doing then is just plugging it into here. And that's going to come out to some number. So about negative 0.67. So L of 3 then should equal negative 6.7 times 3 minus 4 plus 67. So approximately 73.7 volts. Is that okay? Oh, I'm sorry. This was part C already that I did.
So I'm just, why is it saying like,
Hold on a second, please.
oh, sorry.
So what we wanted here, that is, oh, sorry. We didn't answer the question. I got carried away. The key here is rate. So we're just doing C prime of 3. Excuse me. My apologies. Did you ever get carried away? So negative 7.41 volts per hour. And then I think that I just screwed this up. I think this was supposed to be 4 and this was supposed to be C3. What did I write in my key when I did this? Oh, look at this. Look at this bonehead thing here that I did. I said I'm doing C prime of 3. What did I put in there, though? Yeah, Mr. Kulik. It's not your best stuff ever. What was that? Negative 7 point whatever, 41? And then, oops. And that should be okay. Once I change the question to reflect what I meant to be doing. I don't know, did I answer that or not?
Yeah. So it's not as hard as you think. Tangent on 20.
Yeah. It's like the hard part I did for you by giving you the model to define the function. And then, in fact, I didn't even really give you the model. I just said there is a model, and here's the derivative for it. So I did the hardest parts for you. You just had to like use the model or the derivative of the model to get a rate, and then, you know, do the tangent line piece. And realistically, I should have, I think I will update this for future, but I should have asked for time 4 here, and this should be 4, and that should be 3. And then it all, like, you can use your answer from the previous one to do the next one. It all fits together. That's what I was trying to do, and I just didn't check it 55 times, so Mr. Kulik made Mr. Kulik mistakes where he just has, like, the numbers in the wrong spots, and just, I don't know. But that's all that's happening there. It just, like, again, the fact that it was under the 310 stuff, like, all we're doing is building a tangent line to make an approximation, right? I mean, you could do this same stuff doing differentials. I just think the tangent line is like, why build a different thing to do something we already know how to do? You know what I mean? Like, it's doing the same thing. We're just calling it a different name and using like different steps to get it. Like, but why? For a problem like this, if all we were doing is making an approximation, like, let's just use the tangent line, name nomenclature and symbols and process, because we already know how to do it, you know? So that's, I mean, that's the takeaways, that the differentials, everything you can do with a differential, you can do with a tangent line. It just, like, sometimes it's more convenient to use one versus the other. In most cases, the tangent line is fine. They're just ways of doing a linear approximation.
Oh, okay, so.
All right. So again, just want to talk for just a quick second here before you guys go. For the asynchronous days, I made a video for the lectures for 4.1 and 4.4. Now, yeah. I'm sorry, 4.1 and 4.2. Yeah, that's, I don't know, I'm exhausted. Mr. Kulik can't think. Again, if you want to put all that off till after the test, and it's like, that's a, you know, like a Tuesday night problem, I understand. But we're going to be starting like with questions and then starting 4.3 that lecture or that day after the test. So like, yeah, try to do like 4.2 is pretty quick. I think that video is like 20 minutes or something. The ideas are pretty straightforward. 4.1 is a little bit more stuff in it, but the ideas are pretty straightforward.